And usually in the center here, it'll have like a bunch of wires. But basically, it allows you to monitor a larger area than with the end window. So this is your detector area here. The end window, okay, and usually there's like a little metal rod on the inside of the chamber. One of the things that we're going to be learning about gas detectors is that we monitor the number of ions that it collects. So in other words, on the inside of both of these detectors we have some type of gas or air, and when the radiation comes in, it's going to ionize the gas, and we get a positive ion and we get a negative ion. Okay, remember the positive ion is going to be the atom from which the electron was removed. The negative ion is going to be an electron. Okay, on the inside of the chamber, the wire running through the middle of this has a positive charge on it. It's called the anode. The entire outside of the chamber has a negative charge. So what will happen then is the negatively charged electron will be attracted to the wire in the middle, and that's what creates the electrical pulse that tells you that you got radiation. The positive atom will go to the side of your chamber. It'll pick up an electron off the wall and reactivate itself. That make sense? So, and like I said, the sensitivity of the detector is mainly controlled by how much voltage we use to collect these ions. Okay, when we start getting into the actual functioning of these detectors, we're going to talk about what voltage ranges they work in, because that, again, determines their sensitivity. The higher the voltage we use to collect the ions, the more sensitive it is. Okay? Your Geiger counter is typically over 1,000 volts, usually somewhere between 1,000 and 2,000 volts. Your pancake probe up here, usually a little bit less. But again, going back to the stuff that I sent you, okay, this is an interesting question here. Okay, so you're looking for background, and this is the reading that you're getting. Yeah, would you guys be satisfied with doing this? No. Because the problem is it's reading way down here, so you really don't know if it's detecting anything. So what would you do?
Increase the sensitivity.
Okay, increase the sensitivity. So by going to the times 10 and the times 1, what you're actually doing is increasing the sensitivity by increasing the voltage that you're using to collect the ions. Okay? So the other thing is, remember I told you, okay, you need to be able to measure what the radiation reading is. So for example, on this question here, okay, what is your radiation rate here, and is that something you would be concerned about?
Not necessarily. Isn't that background?
Well, let's take a look here. You notice up here we have counts per minute. Now, one of the units that we're going to be talking about this morning when we get through with this is whenever we record something in nuclear medicine, do we record it in counts per minute or do we record it in disintegrations per minute?
Disintegrations.
Okay, disintegrations per minute. So then what's the difference? Or is there a difference? Mr. Viad, is there a difference? There's a difference, okay? Yeah, so you don't know. Monica, what's the difference between DPM and CPM? Okay, Mr. Singh.
Yes. I don't know.
Okay, disintegrations per minute. This is actually in your math book too, guys. page 81. Okay, basically it's counts per minute or GPM is equal to the counts per minute divided by the efficiency of the detector. Now, by efficiency we mean out of a certain number of radiation events that are given off, what percentage of them are actually detected by the detector? Well, it's actually could be worse than that. Okay? The efficiency, let me give you an example of it. Let's say that we have a source of radiation that we know contains 1 microcurie. Normally, a calibrated source of radiation is very expensive because it means that somebody has, looked at it for a long period of time and counted it for a long period of time. So they know that statistically it's within plus or minus 5% of the actual activity that's in it. Okay? So in other words, the only way that you can get a calibrated source of radiation that we use for accuracy checks on our equipment is one that has been released. There's an organization called the National Institute of Science and Technology. It used to be called the Bureau of Standards. You guys ever hear of either one of those? The Bureau of Standards is the one that keeps the weight, the length, everything. So, it's like they have a bar of platinum that weighs 2.2 kilograms, and they use that as a comparison for weights around the world. That way they have an actual piece of something that weighs the accurate weight. Well, the Bureau of Standards was changed, and now we have this organization called the National Institute of Science and Technology. If you order a source from them, it's one that's guaranteed to be within plus or minus 5% of the actual activity. The other stuff that you get is it's a source of radiation, but it's not guaranteed to have the actual amount of activity in it that it states. It's like an OEM brand. Okay. So, from what you remember, a microcurie gives off 37,000 disintegrations per second. So with my calibrated source of radioactivity, if I put my instrument over here, and I monitor the radiation for 1 second, and let's say that I get 16,000, or let's say I get, what's half of that? Let's say I get 18,500 counts per second.